Hi, I am Rahul Prakash and I am a systems engineer in Precision DAC group at Texas Instruments. Today I am going to talk about multiplying digital to analog converters, commonly referred to as MDACs. By definition, every DAC is a multiplying DAC. The input code is multiplied by the reference to produce an output. So why aren't all the DACs MDACs? Well, the difference lies in how much the Vref can vary and what kind of output the output pin provides. For a typical DAC, you need an extremely stable DC voltage reference. However, in some applications such as signal attenuator, where the attenuation is controlled by the digital code, it is useful to have a variable reference. Now, this is where MDAC differentiates themselves. The reference of an MDAC can vary so that it can be substantially greater than the supply voltage itself. The table shows the reference pin limits and the supply voltage for two DACs. One is a string DAC, the DAC 8562, and other is an MDAC, the DAC 8811. You can see the Vref pin for MDAC can vary from -15 to +15 volts, while the supply, the AVDD pin, is at 5.5 volts. The second differentiating feature of an MDAC is the output pin. While most DACs provide a voltage output which is either buffered or unbuffered, the MDAC provides a current output. So, you need an external op amp to convert this current into a voltage output. For simplicity, I will walk you through an example of a 3-bit MDAC. Now, let's take an example of this MDAC with Vref equal to 5 volts, R equal to 1K, and code equal to 110. And let's calculate how much current would flow through the I-out pin for this particular code. Now, to calculate the current flowing into the I-out pin, you have to find how much current flows into the Vref pin first. Well, the current flowing into the Vref pin would be this voltage Vref divided by the equivalent series resistance looking into this terminal. So, the equivalent series resistance looking into this terminal is R. Now, how do we get to that point? Well, typically MDACs would be always used with an op amp. That means this terminal I out would be at virtual ground. So, if you consider this terminal I out at virtual ground, the equivalent series resistance turns out to be 1K or R in this case. Now, an interesting thing to note is for any code, this resistance never changes. That means the reference circuitry for the Vref pin is very easy because the resistance looking into this Vref pin never changes. Now, going back to how much current flows into this Vref pin, it would be 5 volt divided by R, which we calculated, which is 1K. The current turns out to be 5 milliamps. Now, to calculate the current flowing into I out, we have to calculate the current flowing into each of these legs. It's quite easy because at any point along this R resistance, the equivalent series resistance looking outside is 2R. So, using that, we calculated that the current flowing into the MSB leg is 2.5 milliamps, this leg 1.25 milliamps, and these two legs as 0.625 milliamps. Now, calculating the current flowing into I out is quite simple. All you do is sum this current and this current, 2.5 plus 1.25. That gives you 3.75 milliamps of current flowing into the I out pin. Now that I have stepped you through how to calculate the code dependent current flowing into the I out pin, all that is left is to convert this current into a voltage. By using an external op amp as a current to voltage converter, the output voltage ranges of minus Vref to plus Vref can be generated. The RF resistor, which is usually integrated into the chip, is matched to the ladder resistors on the chip. An interesting property of MDAC is that the voltage generated is of the opposite polarity of the Vref pin. Another interesting property is that the DAC output impedance as seen looking into the I-out terminal changes with the code. Now this is an important property because it basically affects the stability of the external op-amp that would be used to convert this current into voltage. So the external op-amp must have sufficiently low offset voltage so that the amplifier's offset is not modulated by these impedance changes on the I-out terminal. Now if the op-amp has a large offset voltage, this can produce significant linearity errors in the transfer function of the MDAC. So MDACs have some interesting properties. However, there are three important things about MDACs that we should keep in mind. Number one is, by architecture, MDACs are current output DACs. Well, that means that an external op-amp is required to generate a voltage output. Now property number two, the impedance looking into the reference pin, which is Vref pin, is constant over entire code range. This simplifies the reference design considerably. Number three, the stabilization of the external op-amp is a little bit complex for the MDACs because the impedance looking into the inverting terminal of the op-amp changes with the code. MDACs are extremely powerful signal processing components. They can be used for noise sensitive application because they provide an option to select a low noise op-amp such as OPA277. MDACs are typically used in test and measurement equipments, but they are not limited to this space. They can also be used as a precision current source and other low noise applications. One of the most common ways to use MDACs is to create a 2 and a 4 quadrant multiplier circuits as shown. For more information on the products mentioned or to ask questions on our Precision Data Converter forum, please visit the following URLs.